This is a brief overview of the main ideas of the paper Fairest Neighbors by my co-author Halvard, Hummel, and myself. The more technical parts of the paper are not discussed in detail here, but you could look at the paper itself for those. The main points of the paper are that existing unfairness measures can be used to search for objects that are fair trade-offs between multiple query objects. So for example, if you are performing a metric similarity search using a metric index and you search for a human and a horse, you might end up with a human or a horse, but maybe what you want is some combination like a centaur. And in this case, you might want some kind of combination that forces this kind of trade-off. And this is what we do with these fairness or unfairness measures. And an important aspect of this is that these queries can be used on existing metric index structures without changing them in any way. You simply have to adapt the query procedure slightly, but not much really. We also show that if we narrow down which kind of unfairness measure we use to a linear case, the so-called weighted ordered weighted averages, we can handle quite general cases, even weirder regions in the index structures. One particular case is if the query is inside a ball and we want to eliminate what's outside the ball, as is the case in the VP tree or the list of clusters, for example, then we're able to create a much better bound for these measures specifically than in the more general case. And we also show that using such combined queries, it gives a higher performance than if you were to simply search for the query objects individually with, let's say, a larger query radius to make sure that when you search for a human, you get the centaur, and when you search for a horse, you get the centaur, and then you can look for the trade-off in the intersection. The point is that those radii will have to be quite a bit larger, and therefore the performance tends to go down, and also you'll have to do multiple queries. So what are these multifocal queries? Well, we base ourselves on two different formalisms that are sort of related. We have the older complex queries formalism and the slightly newer, or quite a bit newer, ambit formalism. But the idea in general is that we produce a vector, a sort of a feature vector for any object that we might be interested in. This vector is just a vector of the distances to the query object. So for each query object, we have one real number. And then once we have these vectors, we apply a function to produce some kind of combined distance or a remoteness. And then we threshold this remoteness using a combined radius to determine membership. So this is a generalization of balls. Most basic example would be an ellipse, where you add two distances together with a radius, but you can have polyellipses, weighted polyellipses, or many different kinds of regions. And overlap with other regions can be determined. For example, if this remoteness function is increasing and we use lower bounds to determine overlap, we can simply insert the lower bounds instead of the actual distances. And if we get a positive membership, then there is overlap. Now, which remoteness function we use, which function we use to create this combined distance or remoteness, has a lot, has a high impact on which kinds of results we get. For example, if we use minimum, we get a very unfair solution because the minimum is a basic fairness measure, and we are minimizing here because we are essentially using the same algorithms as when we're finding the nearest neighbor, when we're minimizing distance, but now we're minimizing this more general remoteness. And if this remoteness is then a fair combination and we're minimizing the fair combination, we get the least fair object, which is the most unfair one. So in this case, we see that we'll end up with objects that are close to one of the queries or the other, but not close to both, not in the middle. If we have multiple query points, we'll have a similar situation. Now, in this sort of scale between fairness and unfairness, we have this straight up utilitarian case, which is neither fair nor unfair, which is simply a sum or possibly a weighted sum, any linear combination. And this is indifferent to any kinds of trade-offs. For a sum, for example, we get an ellipse here where we have two query objects or a metric equivalent. And this is indifferent to where our results lie between these objects. Here I've set the radius to be the distance between the two just to illustrate this very clearly. So the ellipse collapses to just the line between them. And any object on this line is optimal, is as good as it gets. But that's not what we want. We want something in the middle. And we can get that by, for example, using a sum of positive powers above 1, such as the sum of squares, which gives us a, in this case, in the Euclidean plane, it gives us a circle in the middle between the 2 points. And this is exactly what we want. And a sum of powers above 1 is a classic example of an unfairness measure, which is what we're looking for. Now, we could, of course, construct this ball or construct a point in the middle here and do a normal ball query. But the point is, we want to be able to do this in general metric spaces. And in general, we may not be able to construct such a point. For example, if we're doing edit distance between strings, it might be hard to figure out which string is in the middle and so forth. So the remoteness functions we use are then taken from multi-criteria decision-making, classic welfare functions that point in the direction of fairness or unfairness. So by using these, we find fair trade-offs between the distances to the query objects. These existing unfairness measures are already made to be applied to vectors of real values. So it's basically a plug and play situation. A very general and very well-behaved example is the ordered weighted average, or the more general and slightly awkwardly named weighted ordered weighted average. This is closely related to weighted averages. The difference is that the values are sorted before the weights are applied, so that we can give different weights based on whether a value is the minimum or the maximum and so forth. And this allows us to create fairness and unfairness measures. The weighted version also allows us to attach weights to the dimensions themselves, regardless of whether they're the maximum or the minimum and so forth. Here's a sketch of the situation. To the left, we have the Euclidean plane with a query consisting of two query objects, Q1 and Q2. And we have an ordered weighted average ball around them. And we are comparing this to a region R with a center C and a radius lowercase r. And on the right, we have plotted the same situation in pivot space or in focus space. It's the set of these distance vectors or feature vectors. So each coordinate is the distance to one of the queries. And we see that we have upper and lower bounds producing a square in this case, or a box or a hypercube in general around the ball. And because our remoteness function, which in this case is an ordered average, but it doesn't have to be, because it is monotone, we can use the corner corresponding to all the lower bounds, which is the lower left corner of this square, indicated by a plus, and check if that is inside our query region, capital Q. If it is, then we have an overlap with the square. And given that we only know that the metric axioms are in effect and we don't know which metric we're using, we cannot do any better than this. The hatched region here might contain relevant points, even though it does not in this case. So in this case, it gives us false positives, but there's nothing we can do about it. In the other case, with the upper bounds, that's the upper right corner, also indicated by a plus. If that's inside, then we know the entire region is inside the query, so we can simply return everything. So all of this we get for free as long as the remoteness function, or the unfairness measure, which we are minimizing, is monotone, that it is increasing. Now we have an additional twist. It might not be a great difference to how things are done, but it's still an improvement for the cases where, for example, we wish to determine whether the query is inside a ball, such as in the LC structure. It's also relevant if we wish to detect overlap with more general regions represented by other linear ambits, just like the query. Because if the query is represented using a weighted ordered weighted average as the remoteness function, it can be represented as a linear ambit. And we know how to detect intersections between linear ambits. It is described in separate publications. A linear ambit is a polyhedron of query object distance vectors. So it's a polyhedron in pivot space. And we can efficiently determine intersection with this polyhedron, even though for the weighted ordered weighted average, as well as the weighted ordered average, we have a factorial number of facets, but because of its shape, we only need check overlap with one of the facets to determine, for example, intersection with the outside of a ball, which is what we need in order to check if the query is completely inside the ball. So for this query in region case, we can actually get an arbitrarily large improvement in the bounds used compared to the basic monotonicity formalism. So we've done some experiments, rather limited experiments, but they're a beginning at least. We use 2 object queries with an ordered weighted average, with weights of 1 and 3 as in the well-known Gini coefficient. And we apply this to the list of clusters, or LC. We find the fairest neighbors, k fairest neighbors, using k from 1 to 5. And we average the results over 100 query pairs. We have synthetic data, so 100,000 uniformly random vectors and 100,000 clustered vectors, Gaussian clusters. We use dimensions 2 to 10. Might, of course, have had higher dimensions, but the main difference would be that we would need to fine-tune our index structure rather than the formalism. So we postponed this to future work. We also have real-world data sets from SISAP. We use the colors in the NASA and Listeria sets with the edit distance for the Listeria strings and Euclidean distance in general. As a comparison to our method, we also use a more straightforward method where we search for each object individually with a radius sufficient to find the trade-off object or objects. This is, of course, somewhat artificial because this radius is not known if you haven't already found the trade-off objects. But the result of this is merely that we get conservative estimates of our performance relative to the competition. And what we found is that in this case, we get a speed up of about 2. So that essentially means that what one might expect, more or less, that we're performing a single query rather than 2 queries, and therefore it's twice as fast. So for multiple query objects, we might get higher speedups. We also get a speedup of about 4 compared to linear scan, though that's perhaps less interesting, as that's more a measure of how good the index structure is, which is not the main focus.